Carl Sagan says we're made of star stuff. But right after the Big Bang, there were no stars and no stuff. No carbon, oxygen, iron, or any heavy elements. So how did that happen? How did we go from a structureless gas of just hydrogen and helium to a structureful universe of stars and planets and galaxies? And the whole periodic table of elements, almost 100 of them. So that's what we're going to look at today in episode 3 of How Everything Evolved. We're going to go from just after the Big Bang, 14 billion years ago, through just before Earth, around 5 billion years ago. Let's do it. So today's episode of How Everything Evolved is a cool one. Looking at star formation and how we got the periodic table of elements. It's really quite cool. So let's start, as we always do, with the timeline. And so we're going from, 14, here's the start of time, here's now. And we are going to start with, here's 14 billion years ago with the Big Bang. And last time in episode 2, we looked at this little period here, from the start of the Big Bang until 1 million years ago. And that was an interesting time, and it was when we got atoms. And today what we're going to look at is right here, 4 billion years ago is when we got the sun and the earth, when our solar system formed. And so we're going to look at this period of time today. It's about 10 billion years in here, just a small period of time, And what we're going to do is at the beginning, it's pretty interesting because at the beginning, we just have hydrogen and helium. And then by, 4 billion years ago, 5 billion years ago, we have a whole periodic table of elements, and we have stars, and we have planets, and we have galaxies. That's a spiral galaxy. So how the heck did that happen? How did we go from structureless gas to a structureful universe of all the periodic table of elements? And the answer to this comes kind of twofold. One of which is, you have to have gravity to make stars and planets. You get these blobs that form through gravity. That process of gravity and star creation actually leads to the periodic table of elements through fusion in these stars. So we're going to chat about both of those today. And let's start with gravity. So gravity. Define gravity. If I was a good singer, I would sing that song, or I would do the soundtrack for the movie. But I'm neither a good singer nor am I a symphony. So we're just going to talk about gravity. Gravity it's interesting because the main thing that it does is when I think about the universe over time, you can kind of break it down into these different libraries. And how everything evolved is we're going to look at these different libraries. And the first library that we're looking at is the library of atoms. How did the atoms form? How did they combine with each other? And then eventually we're going to look at genes and ideas and code, these big 4 libraries. But, zooming in on Library of Atoms, I like to think of it as having 2 floors. Let's make that a better square, huh? And so the first floor is small things. And so that's atoms. And then the second floor is bigger things like stars and planets. And you can imagine something above that, galaxies and filaments and all those things. And at the atom level, as we chatted about last time, that's mostly determined by the electromagnetic force, where you have electrons rotating around, orbiting around protons. Stars and planets, though, that is mostly gravity. And so they're 2 different forces that kind of control microstructure and macrostructure, and they operate essentially the same way, which is a sheet, and then that sheet makes these orbiting blobs. And the reason for that is because the closer you are, because the electromagnetic force and gravity are a function of distance. That's why we get these orbiting blobs. And this helps us begin to understand our friend here, the Standard Model. I always love to bring up the Standard Model. And, last time we chatted about how up and down quarks make protons and neutrons. And so we started to understand that. We learned how to ignore the second and third columns here because those are just heavier versions of these things. Last time we also chatted about electrons and how electrons are those things that orbit around atoms. And so we started to understand the generations of matter here with these fermions. And then for the boson, we looked at, gluons and how gluons are the strong nuclear force, essentially the glue or the Velcro that sticks together up and down quarks to create protons and neutrons. And we also looked at photons and how photons kind of carry the electromagnetic force. They're kind of the particleized version of, the electromagnetic force is very strange. It can be waves sometimes, it can be particles other times. And so the photon's kind of the force carrier for that. And today, gravity, if we're just going to talk about gravity, and gravity is this graviton. Graviton is hypothetical. And again, this is above my pay grade. This is into particle physics. But I think it's a hypothetical boson where we think, we've seen gravity waves. We think that there should be something like a graviton, some kind of particle, a force carrier for gravity, but we haven't found it yet. But it's here on the standard model anyways. So that's later today we are going to understand W and Z bosons, which do the weak nuclear force, and then we'll also be able to understand electrons and the electron neutrino later today. Okay, so that is gravity, and gravity brings these items together. The more massive they are, the more gravitational forces on them, which is why you feel pulled down into the earth, but I don't feel that much pull towards my microphone or whatever. Gravity, what it starts to do is at the beginning of let's begin to talk about star formation. So stars. Start with this early universe, and that early universe is 75% hydrogen and 25% helium. And over time, gravity, if at the beginning these things are kind of sparkled around, over time, gravity starts to bring things together until you get things that look like stars. If we go back up to the timeline, there's a period of time from roughly after the Big Bang, technically after recombination 380,000 years ago, through about 150 million years after the Big Bang. That's called the Dark Ages. The cosmological Dark Ages. During this time, there was no solar fusion happening. It was just the hydrogen and helium atoms were slowly starting to come together. And then over the course of the next billion or so years, the universe started to light up because we started to have solar fusion beginning to occur. So that was a pretty beautiful moment. And the way that solar fusion happens is, it's kind of an interesting thing. So you have, what you're trying to do is you're trying to get from hydrogen to helium. Because remember that the periodic table is just an increase in the number of protons each time. So hydrogen has 1 proton, while helium has 2 protons and also just 2 neutrons. And so the question is, how do we fuse hydrogen together in order to get helium? That's kind of the question of the day. And there are 3 different ways that we can create bigger and bigger elements. And we're going to start with the first one, which is called the proton-proton chain. Proton-proton chain. And as you can tell there, it's going to be combining protons together. And so what it does is, the way I like to think about this is you can imagine there are kind of 2 ways to combine. So you can say, okay, maybe I have 1 proton, and you're being something like the sun is crazy, has 10 to the 58th protons in it. So that is a lot of protons, and so they're being shoved all in there. And the question is, okay, maybe if you just shove 2 protons together, does that work? Not really. That's called a diproton. It is not long for this world. It goes away fast. You can't have a diproton. It just immediately dissipates. What you can do is go the other way. You can say, let's make a proton. Let's combine a proton and a neutron. That works. And then you can maybe combine 2 of those to then create a helium atom. The issue is that, where are the neutrons coming from? And so you're trying to create a proton plus a neutron. Where the heck is the neutron coming from? We need to turn a proton into a neutron. And so we have a super proton-rich energy in there, or super proton-rich environment, and we need to start to turn some of those protons into neutrons. And the way that happens is through the weak nuclear force. And what it does is it either turns protons into neutrons or neutrons into protons. And right now we're going to talk mostly about protons into neutrons. Later we're going to talk about the other way. But so we're moving protons into neutrons. The term for this is beta decay, and specifically beta plus decay. The other way is beta minus decay. And what it does is, essentially, and you can see it here on so this happens through the weak nuclear force, and it's going to be this W boson here, W for weak. And the Z boson is also a weak nuclear force thing, but we can essentially ignore it. So this W boson represents the weak nuclear force. It's the final force that we haven't chatted about. By the way, we've talked about gravity now. We've chatted about the strong nuclear force. We chatted about electromagnetism. And now this is the weak nuclear force. So it's the strong nuclear force, which velcros things together. And the weak nuclear force turns protons into neutrons, or vice versa. And so this weak nuclear force, what it does is it turns protons into neutrons. It takes a long time for that to happen. Protons don't really want to turn into neutrons. If we think back to what protons and neutrons actually are, protons are 2 up quarks and a down quark. and neutrons are one up quark and two down quarks. Essentially just turning one up quark into a down quark. For reasons that I don't totally understand, it takes a long time for that to happen. The average proton, there's so many protons hanging out, and eventually they do want to turn into a neutron. So you can imagine this is deep inside the sun. There's so many protons, so many protons. The average proton, the average amount of time it takes for the average proton to turn into a neutron, it's so long. It's 10 billion years. And so this is, it's just waiting. It's waiting. And then eventually it turns into a neutron. And then we're like, oh my God, finally now we have our proton and our neutron, which we're so happy about because those things are combined into, that's called a deuterium nucleus. And then that thing you can combine with another deuterium nucleus, and boom, you get helium. That's helium. So this is how it happens. And we have, the thing that I want to emphasize here is this is a really cool barrier to dissipation. The sun, if we imagine our good old sun here, and here's our little Earth, this thing has been around for 5 billion years. It'll be around for 5 billion more. And the reason why it doesn't all just immediately collapse and turn into helium and stop burning is because there's a barrier to dissipation. Each proton doesn't really want to turn into a neutron. It's kind of lazy. It's like waiting around, being like, maybe what about you? Wait for a while. And because of that allows for something like life to form. And so you can kind of think of it like a dam. You don't just allow the dam, all the water to rush through it immediately. Then you just lose all of the energy. And so we kind of need this barrier to dissipation in order for photosynthesis to emerge, in order for animals to emerge, in order for us to kind of take the beautiful gift of the sun that we have for these 5 billion years. Or really 10 billion years. So that is how this thing works. I think it's also worth showing a different image of this. So you can see, here's a traditional Wikipedia picture of the proton-proton chain. And you can see the stuff that I was chatting about earlier, which is, you have these hydrogen protons, essentially, and the protons are there, they're waiting, this is the long step where they're waiting. Eventually, they turn into this deuterium, this 2H here, where you have a proton and a neutron. They wait. Eventually that happens. Once that happens, then boom, another hydrogen immediately clicks onto it. I didn't really talk about this step, but for a little bit of time, they become an H3 atom. It loses then its two bonus hydrogens and then turns into a helium. And so you have these two different chains doing roughly the same thing, eventually turning into helium. So that is how solar fusion works and how the proton chain works. And this is as you can see here, the other note here is you see this little thing here that says neutrino. A neutrino is the final thing in our standard model. Bottom left here, a neutrino. Neutrinos are crazy. They're the final thing that we should need to talk about here. Higgs boson, we don't really need to talk about that. We spent a long time trying to find it. It's a provider of mass, but not we're talking about too much today. And so we've filled out our whole standard model. And so with the neutrino, so a neutrino is we get a ton of them from the sun. They are one of the crazier particles. Other particles, neutrinos are crazy because they have 500,000 times less mass than electrons. So they are essentially massless. And so they don't really interact with gravity as a result. They don't have any charge, and so they don't interact with electromagnetism. They only interact a little bit with the weak nuclear force and a little bit through gravity, but almost none because they're almost massless. And so that's why we're constantly being bombarded. The sun is producing tons and tons of neutrinos at any moment, and we're constantly being bombarded by something like, I forget the number, 10 to the 20th neutrinos per centimeter squared or something. They just go through everything. They go through the center of the sun. They immediately get out. They go through the center of the earth. We use them sometimes to detect things in the middle of the earth. And they're just kind of shooting through the universe, being neutrinos. So that is the proton-proton chain. And those are barriers to dissipation. And what I want to talk about now is how long, when this happens in the sun, the weird thing is that the light that we get from this, it takes a really long time. It took 10 billion years for a proton to turn into a neutron. It was waiting. And I want to talk about a few things. The first thing that happens is when this happens, energy is released. And so when you go from a hydrogen atom to a helium atom, you go from one proton to two protons and two neutrons. And you actually lose a little bit of mass in this transition. And that mass loss is actually what creates energy, and it gets pushed through E equals mc squared. And what you have every second, I believe, in the sun is turning 600 million tons of hydrogen, and it's turning that into 595 million tons of helium. That's crazy. So much fusion happening. And so there's a 5 million ton difference. And that 5 million ton difference is pumped through E equals mc squared and turns into the energy that we know and love today. And so that is what's happening in the sun. And when that energy pops out, it takes a long time for it to get out, actually. So you can imagine that energy is mostly in the form of a gamma ray. Back to this image over here, you can see there's the gamma ray, that little Y thing there. So it takes a long time for that gamma ray. It essentially goes through a random walk, kind of like it's in a corn maze or whatever. And it takes about 100,000 years for that photon or for that gamma ray to slowly get out of the sun. And then eventually, boom, once it gets out, then it takes 8 minutes to get to Earth. So that's kind of interesting. It takes 10 billion years for the average proton to turn into a neutron. Once that happens, it takes 100,000 years for the photon from that thing, the gamma ray, the really intense high energy particle, to bounce its little body around there. As it does that, the energy gets dissipated, so it turns from a gamma ray or an X-ray, a really intense thing that would damage us, into what we know and love, which is a little bit of infrared, a lot of visible light, and also some UV light. And so it decreases in energy and then turns into something that's more palatable to us here on Earth. So that's fusion. That's the main solar fusion, how that works. And now what I want to talk about is the next step in that chain. We're trying to go from, the issue is that, if we look back to this, here's like a periodic table. We've done hydrogen, and we know how we get from hydrogen to helium. Some of that happened during the Big Bang nucleosynthesis, 380,000 years after the Big Bang. But then a lot of it happens in these stars where you're turning hydrogen into helium. What about the rest of the periodic table? And so now we're going to talk about the next big way that we do that, which is called the alpha process. And the interesting thing about the alpha process is we can't just, for reasons that are beyond my pay grade, in theory, you might be able to say, oh, we have a helium here. Can't I just take that and turn it into lithium? Can't I just add an additional proton and an additional neutron and turn it into lithium? That's not really how it works. The reason why what we actually do in order to get the further and further elements is we shove new helium particles onto them. We shove helium particles together. So at the beginning, we were combining 1 + 1 = 2, and now we do 2 + 2 = 4, and then 4 + 2 equals 6. And so that's how we produce this. If you take helium, which is 2, actually, let's show this on the periodic table itself, where you have, here's hydrogen, here's helium, here's lithium, here's beryllium, here's boron, here's carbon, here's oxygen. Helium is 2, and then lithium is 3, beryllium is 4. For various reasons, we can't go directly to beryllium. It's not that stable. So we kind of skip boron as well. But we go to carbon, and then to nitrogen is 7, and then oxygen is 8. Happens here is you have, and it's called an alpha process because the helium atom is just called an alpha particle. There's alpha particles and beta particles, and we talked about beta decay. Alpha decay is when you lose a helium. Alpha fusion, or the alpha process, is when you gain helium. And so what this looks like is, you're taking a helium atom and you're taking this 2 proton, 2 neutron thing, you're combining it with another one, and then you're combining it with another one, and then what you get out is carbon, aka a 6 proton thing with 6 neutrons. And then what you get to do is you get to keep on adding 2 each time to get bigger and bigger atoms. And so if you want oxygen, you get 8 protons and 8 neutrons. And you can keep on going all the way up until, and we'll talk about why it stops here in a second, you can go all the way up until iron with 26 protons, and it usually has a couple more neutrons. So that is the alpha process. And I want to show a picture of the alpha process here. it is, yeah, you can see all the processes actually. You can see the proton-proton chain in the top left corner here. So that is what we already talked about, where you're combining hydrogens together to get helium. We didn't talk about the CNO cycle, but it is a way that bigger stars essentially they do hydrogen fusion. So you're taking hydrogen, you're combining it with carbon, which turns into nitrogen, which turns into oxygen, and then that eventually shoots off a helium. So it's kind of a faster way to make helium from hydrogen using carbon, nitrogen, oxygen as intermediates. And then here's helium burning, the triple alpha process. So at the beginning, you're taking a few heliums and turning them into carbon. And then later you're doing what we just showed here, where you're taking carbon, turning it into oxygen, to neon, to magnesium, all the way up until iron. So that is, and then in a second we'll talk about the R process and S process down here. But yeah, that's the alpha process. And yeah, it has a whole bunch of implications. It means that not odd, but even elements are more likely in the universe, which is kind of interesting. And yeah, it also happens, the crazy thing about this is that it happens in the last years of a star's formation. So the star spends most of the time on the main sequence, just ripping through hydrogen like our sun is doing. It's just turning hydrogen to helium for most of the time. And it'll do that for, 10 billion years. And then only in the last year of its life, it'll then say, okay, now I'm ready to do helium. And I'm just going to go through helium super fast. I'm going to speed run. I'm going to turn helium into carbon. I'm going to turn carbon into oxygen. And each of those steps is even less and less time, where the amount that does silicon burning or whatever is just the final 10 minutes or whatever. So that's how that works. And then usually that thing will explode. And then that's how we get all the elements. That's the we are star stuff idea. Okay, so now let's talk about why it stops at iron and how we do the next part of this. So, if you imagine what we had thus far is a thing where the force of gravity is allowing us to essentially allows us to have the strong nuclear force overcome where you have all of these freaking protons, and the protons don't really want to shove together. But if gravity pushes them together enough, then boom, the strong nuclear force takes hold and they get Velcroed together. So that's kind of the mechanism that we had thus far. And the issue is that as you have something like iron, which has, these 26 protons, also these 30 neutrons, it's got a lot of, it's got a big old nucleus there with all these protons in there and all these neutrons in there. And that thing, it's kind of happy because it is, Velcroing together all these things, but the protons, they don't love it. And so when you try to shove an additional proton in here, when you try to create something like nickel and you're like, okay, just add an additional alpha particle, add an additional helium in there, it's like, bro, I already got way too many protons in here. I can't have 28 in here. And so it doesn't want to, so the alpha process essentially stops. It says, look, everything up until this point released energy, but now this is going to take energy for me to add protons here. There's too much, essentially at this point, the electromagnetic force is then again greater than the strong nuclear force, where it says, look, I'm not going to shove additional protons on here. So that's why it stops at that point in time. And so that brings us then, so the question then is, okay, well then how do we produce stuff like gold? And gold has 79 protons. And so how do we produce these heavier elements that have even more protons in them? Okay, so let's talk about the third way that elements are formed, which is through neutron capture, essentially. And so let's show this over here. And I always, neutron capture. I always am confused. Do you put the I before E except after C? E before U, especially in neutron. So neutron capture, the idea is we're trying to turn something like iron. And iron has 26 protons and 30 neutrons. And remember that the reason why it has more neutrons is because the protons, they don't really want to be with each other because of the electromagnetic force. Two positive things reject each other. And so you need more neutrons there with the Velcro. You essentially need more Velcro in there to counteract the strong nuclear force in order to counteract the electromagnetic force repulsing the protons away from each other. So that's something like iron. And we're trying to turn iron into something like nickel, which has 28 protons and 32 neutrons. And actually, really, there's cobalt in between, which is 27 protons and 31 neutrons. And so what we need to do is we need to add these protons onto there. But The way that this happens is actually, instead of adding the protons directly, we add more and more neutrons. And then once you add those neutrons, eventually those neutrons go, okay, there's too many of us around here, I'm going to become a proton. It's actually the reverse of earlier we talked about in fusion, solar fusion, protons go to neutrons. This is through the weak nuclear force. This is through beta plus decay. And if you have a really proton-rich environment, eventually they'll turn into neutrons. And this is the reverse of that we talked about, but actually the weak nuclear force can operate the other way. It can go from neutrons to protons. And when it does, that's called beta minus decay. When you go from a neutron directly from a neutron to a proton, when you go the other way. And so what we need to find essentially are an environment where we need to find essentially in a neutron-rich environment so that you can start aggregating these neutrons so they can start forming onto these nuclei. Yeah, and so this happens in two ways. We're looking for these neutron-rich environments, and there's one called an S process where this happens, which in S stands for slow, and then it also happens in an R process. And R stands for fast. No, R stands for rapid. In a slow environment, this is in these what are called asymptotic giant branch stars, essentially big old Betelgeuse-like stars that are really big. They've done all their hydrogen burn, so much of their hydrogen burning. They're starting to do a lot of helium burning. The helium is turning into carbon, so there's lots of carbon. And that carbon then starts to get some neutrons on. And so we start to get more. There'll be pockets within these big old stars that are neutron rich. So you'll have a neutron rich pocket where you have a bunch of these little neutrons around there. And there'll just be bonus neutrons around. And then if you have, for these stars, you'll have some of these seeds, these iron seeds, which will be this 26 protons and 30 neutrons. And then it'll grab a neutron. And it'll maybe grab another neutron. And so you'll go up to 31 or 32 or 33 neutrons in order. And then eventually, once you get enough on there, then it'll say, okay, that's too much. And then it'll do that beta minus decay will turn the neutron into the proton. And so then it'll turn from iron into cobalt. And so this is not how the really big ones like gold are created, which has 79 protons, but it's how a lot of the middle ones, 27 through 50-ish, how they're created through a slow S process in these big stars through these neutron-rich pockets, getting some neutron capture, and then using the weak process, the weak nuclear force, to do beta minus decay to turn neutrons into protons. So that's the S process. And you can see, let me show an image of that here actually, where there's let me zoom in. And you can see here that the x-axis is number of neutrons, the y-axis is Z, which stands for the number of protons. And you can see we're at silver that's going to cadmium or whatever. And cadmium's adding on neutron capture, heading to the right, heading to the right, heading to the right. And it's okay, I'm no longer stable. I have too many neutrons. I'm going to do a little bit of beta decay, turning one of my neutrons into a proton, and now I'm indium. And then it'll do the same thing, and indium will then go to 10, and then 10 adds a bunch of stuff, and then goes again. So this is kind of the process of the slow process. And you can see another version of that image here, where you're adding neutrons, and you're adding a couple neutrons, turning into protons, adding a couple neutrons, turning into protons. So that's how the S process goes. And now we're going to talk about this R process, the rapid process. So an R process, again, we're looking for a super neutron-rich environment. And this usually happens in supernovas. We used to think it happened mostly in supernovas, but we later learned supernovas that actually mostly happens in neutron star combination. There's a better term for that, but neutron star fusion. And so neutron stars are places that have lots of neutrons, obviously, and supernovas too. So what happens in these places is there's so much mass. It's so crazy. Supernova is such a crazy experience where what you have is you have protons, and if you have a proton, you can actually combine it in a very crazy way. You can combine a proton plus an electron to produce a neutron. This is called electron capture. Electron capture. It produces random other things as well, plus, and because you need to balance the books or whatever. And so electron capture, you're taking a proton-rich environment and turning it into a neutron-rich environment. And so you get a ton of neutrons here. And then what will happen is roughly a similar process as this slow capture thing, but instead you'll just have tons and tons of neutrons in an exploding supernova or in one of these neutron stars, and they'll just be everywhere, and you'll be able to very quickly create these big old blobs of just neutrons velcroing onto each other with a strong nuclear force and turning into something like iron. And it'll turn into something where it has tons and tons of neutrons, and then eventually those neutrons will slowly, then through the beta decay, turn into protons, turning into iron and turning into uranium and all these big elements. So that's how our process works. And overall, you can see that there's so if we look back over here, you can see that we know that traditional just proton-proton chain create turn hydrogen into helium. That's what's happening in our star right now. It's going through all of it's about halfway through all of its hydrogen, turning that into helium. And then we start to take, in bigger stars, they take that helium and they do helium burning through the alpha process, where they combine 3 heliums together to get carbon, and then you combine carbon, then you add additional heliums to get oxygen and neon, bigger, all the way up until iron. And then at that point, the gravity is not enough to overcome. There's too many protons in there, and so they don't really want to be combined anymore. And so you have to Velcro more neutrons in a different way, and you do that through these neutron capture environments and these neutron-rich environments, either through the S process or the R process, to create all the rest of these elements all the way up until uranium down here, which is plutonium, is 94, has 94 protons. And that's the biggest element naturally created. All the ones after that, the 118 total elements, are just created by humans in labs. And so that's how this whole thing works. It's a pretty cool thing. And I guess just to conclude here, so today we started at the beginning in these dark ages. And the dark ages, we got the first atoms, but it was just we were chilling. It took 150 million years for all the atoms to come together and to actually start the first process of gravity, and then to start this first process of solar fusion and to light up the universe. And actually, this is a very cool moment where, let me show this other image here, where this is over time, how much this is time since the Big Bang. So today is on the right side, and on the left side so the right side is today and the left side is the Big Bang. And this is the amount of SFR, stands for stellar fusion or stellar formation rate. And so this is how many stars are produced over time. And so at the beginning right here, this is what's called cosmic dawn, happened right after the dark ages ended, 150 million years after the Big Bang / a billion years after the Big Bang. And then cosmic noon happened a little bit after that, where the rate was super, super high, kind of like 10x more than it is today. And you had this beautiful moment where you had cosmic dawn, 150 million to a billion years ago-ish. That's when you started to have, initially you just had just only gas. And then that gas started to form together with gravity into these stars, and those stars started to do the first fusion, and the universe lit up. What a cool moment, where you just have these little pockets of, it reminds me of that scene from Lord of the Rings where they say the beacons are lit. Things start to get lit at this time. On a Friday night, baby, it was starting to get lit. And cosmic dawn occurred, and then a little bit after that, then we get cosmic noon, which is 100 billion years after the Big Bang. This is roughly 12 to 13 billion years ago. While cosmic noon happened, let's call it 12 to 10 billion years ago, where you get not only was it the little bits of star formation, but it was crazy. Stars were forming all over the place at 10x, 20x the rate that they're forming today. And that's what's on this graph here, is that cosmic noon happening. So that is let's go back to this. So that was the proton-proton chain. Then we had alpha processes creating rest, and then neutron capture. And I think I just want to say that we talked about these barriers to dissipation earlier, and how we live today because there's a barrier to dissipation, because it takes so long to do this decay from a proton into a neutron. It takes 10 billion years or whatever. So it's waiting to turn that proton into a neutron, which is why it takes so long for the sun it's been going for 5 billion years, and it'll go for another 5 billion years, because it doesn't just immediately happen, because there's this barrier to dissipation. And in addition to that, I want to say that there's all of these parts. The other barrier to dissipation, which is really cool, is on the periodic table, where you have all of these, essentially all these little stable forms of 1 proton and 2 protons and all the way up 3 protons, 4 protons, all the way up to 94 protons. And the amount of protons plus the amount of neutrons, they're just there to hang out and they like to exist. And it's just crazy that we have 94 stable elements. And technically it's a little bit less, but we essentially have 94 stable elements that are game to hang around. And we're created by all these things, especially all the organic ones over here: carbon, nitrogen, oxygen, phosphorus, sulfur, but also stuff like silicon and stuff like iron. And these things are crucial for planets. They're crucial for life. And the fact that we have these stable, that there are barriers that stop it from being all iron. It would be a boring world if it was just, if it stopped at the beginning. We're just like, sorry, we only have hydrogen and helium. No, we got the rest of the periodic table, and it didn't just all become iron. It didn't just all become something. They said some of the stuff is going to end up as carbon, some of the stuff will end up as iron, and we'll have these 94 total, 94 real elements. So I think that's a really cool way to think about our creation as a species and our creation as a universe. And the other thing I want to say here is that, as we conclude, is if you think about these, we had the Dark Ages, we had cosmic dawn, we had cosmic noon. Over these 10 billion years, you're getting what's called increasing increasing metals, where you're getting heavier and heavier elements. It's not just hydrogen and helium, but you're getting carbon, oxygen, whatever. And so that can then form into these rocky planets. And what we get is, for something like the Earth to form, to tell you about what we're going to talk about next time, you have a star, and then you have us, our little Earth here, and the Earth has a bunch of important things. One of the first things it has is H2O. Also, it's a solid planet that has a bunch of iron in the middle, and so it has a bunch of iron that allows it to iron and magnesium and silicon, so it allows it to have this actual solid thing, and that solid thing is the right distance away, and it can then have hydrogen and oxygen combined to form a liquid. Before this, we just had gas, and then we got a little bit of solids, and then stuff like iron here, but the important thing is that we have liquid. And so you have H2O on these little Goldilocks planets that turns into a liquid, turns into liquid oceans, and then you get carbon. And carbon's a very special element because it starts to form these carbon chains. And those carbon chains are the basis of all of metabolism. They're the basis of all life. And that's how we start the origin of life. So that's what's going to happen next time, is we're going to say, okay, we've created this environment where you have carbon chains in water on a solid planet ready for life. And that obviously wasn't possible 14 billion years ago. It only happened as the result of increasing metallicity and all this solar fusion that was able to create iron, that was able to create H2O, oxygen, that was able to create carbon. So that's what's going to happen next time. And as always, thank you for watching and listening. I appreciate your time. Curious what you think about this. If you have any questions, comments, concerns, put them in the comments below. Or if you have ideas for future videos, we're going to continue talking about how everything evolved. And I also want to thank my patrons on Patreon for supporting me, and also Root, the supporters of Root, for supporting this educational content. So thanks again for listening and for learning about how we got the periodic table. Bye. Thanks.